All right, guys, we're going to start Chapter 6 today. Chapter 6 is all about chemical reactions. So I've got a few pictures up here that remind me of chemical reactions. This is where you mix one chemical with another one, and it reacts, and it forms something new. So this is finally, we're getting into some real chemistry here. But does anyone know what this is right here? It's a firefly. What's the cool thing that fireflies do? They light up. Yeah, they do a chemical reaction in their butt, and it glows at night. Isn't that crazy? Isn't that crazy? They're doing a chemical reaction that produces light. This is a jellyfish. Same thing. It's doing a chemical reaction and it releases light. What are these, guys? Fireworks. Fireworks are chemical reactions. That's all they are. Different elements. They package in these fireworks, and then when it blows up, it gives them energy. The electrons move up to a higher energy level. When it comes back down, it releases light. How much energy it comes back down determines the color of light that's given off. So fireworks, it's just chemistry and chemical reactions. We're going to learn for the first time chemical equations, how to balance them. And we're going to do a lot with chemical equations, how to write them, how to balance them. And so this is finally, we're getting into some real chemistry. We've got a good lab this chapter that you'll like as well. Sort of. We're going to make a hydrogen balloon, and then we're going to blow them up. So
we're going to fill it up and light it on fire too.
That's right.
Awesome. That's so cool.
Okay. Chemical reactions. So please be following along in your guided notes, Chapter 6. Chemical reaction, you're supposed to write down the definition. This is one of our vocab words. A chemical reaction is the process by which the atoms of one or more substances are rearranged to form different substances. So it is the process by which the atoms of one or more substances are rearranged. So the atoms get kind of mixed up. They get rearranged. And you form something entirely new. You form a new substance. And that's what's cool about chemistry. We can take substances, react them together, and make something new entirely. And that's pretty cool. Some examples of chemical reactions. You're supposed to write down 4 of them. Digestion, the breaking down of food. As soon as you put food in your mouth, there's chemical reactions taking place on that food to break it down. And by the time it gets down into your stomach, there's a bunch of acid in there. It's breaking it down even more. It goes into your intestines. We're extracting all of the good things from that food, but it's through chemical reactions that digestion works. Cellular respiration and photosynthesis, 2 of the most important chemical reactions in the planet.
So is that 2 and 3?
Cellular respiration and photosynthesis, number 2. Without photosynthesis, we wouldn't have plants on the earth and we wouldn't be here. So, and cellular respiration is how we get energy. If you remember from biology, cellular respiration and photosynthesis. All right, number 3, gasoline is converted into energy to run cars. So you just put gasoline on number 4 or 3. And number 4 is cooking. Whenever you cook food, you are doing chemistry. You are doing chemical reactions.
What happens when they put salt on the road?
Salt on the road is not a chemical reaction, but there's some good chemistry going on there. It's a physical process. Yeah, it's a little bit. Melts the ice, right? Good. Okay, so digestion, cellular respiration, photosynthesis, burning of gasoline, and cooking food. All of those are examples of chemical reactions. All right, so there's 5 signs that a chemical reaction is taking place. You're supposed to know them, and I'm going to test you on each one of these. So sign number 1, if there's a change in temperature, that's a good indication that a chemical reaction is taking place. So a change in temperature. If it gets warm or if it gets cold, if the temperature changes, that's a good indication. Change in color. Yeah. Like the penny, the golden penny lab, we saw the color change a number of times. Look at this example down here. We've got a clear liquid and he's pouring it into a clear liquid in this beaker, and when it hits, it changes color to yellow. It's a color change. It's a good sign that a chemical reaction is taking place. All right, number 3, if there's an odor that is produced, if it smells different, that's a good indication that a chemical reaction has taken place. Gas bubbles. If you mix two things together and it starts bubbling up, that's a good indication that a chemical reaction is taking place. And finally, number 5, the appearance of a solid. If you mix two liquids together and you form a solid, that's an indication that a chemical reaction is taking place. So any one of these 5, you've got to know all 5. Okay? So let's review them. Now try not to look up there, but what are they? Change in temperature, change in color, odor, gas bubbles, and the appearance of a solid. The appearance of a solid, number 5. Okay, practice problem number 1. I want you to tell me whether these changes, I've got a number of them, like 8 changes here. I want you to tell me whether it's a physical change or whether it's a chemical change. Now, how do you know the difference? A chemical change will form something new. A physical change just changes its size or its shape, but it doesn't form anything new. Let's see if we can get the hang of this. Number 1, burning a log. Is that chemical change or physical change?
Turns to ash.
Okay, you have this log, you burn it. Do you have a log anymore? No, you've got all this smoke, you've got the soot. Isn't it changed? Didn't you make something new? That's chemical, okay? That's chemical. You can't go back and get that log anymore, can you? It's smoke and ash now. Okay, what about melting ice? What is ice? It's water, but it's frozen. So when you melt it, isn't it just going from solid water to liquid water? It's still water, that's physical. Guys, phase changes are always physical changes. So if it's just going from a solid to a liquid or to a gas, if it's just making phase changes, that's a physical change. Number 3, cooking a steak. We just talked about you cook something, you're doing chemistry, so that's what? Yeah, you're doing a chemical change on that steak. It's something new. You're changing the way the atoms are arranged on that steak. Number 4, breaking a stick in half. So you have a stick and you just break it. That's physical, yeah. Isn't it still a stick? It's still a stick. You're not changing how the atoms are arranged. You're just changing its shape or its size. That's a physical change. Number 5, boiling water. Physical. How come? Isn't it still water? Now it's, instead of in the liquid phase, now it's what? What do we call water in the gas phase? Steam, right? Or, yeah. So it's still water. It's a physical change. Number 6, making a pancake. Whenever you cook, you're doing chemistry. So that's what? That's a chemical change. Number 7, a firework exploding. Chemical, yeah. You're going to notice whenever you burn something, that's a chemical change. It's a chemical change. Yeah, you're changing the way the atoms are arranged. Number 8, a solid candle wax melting. Physical. How come it's physical? Good. It's still the wax, right? I mean, it's just now it's going from a solid to a liquid. It's just a phase change. Okay, so hopefully that kind of makes sense. The difference between chemical and physical changes. You've learned about this since when? 3rd grade, 4th grade? chemical, physical changes.
Yeah.
So,
No problem.
yeah, if it changes shape or size, what is it? Physical. Like if I take this paper and I do this, what is that? Just rip it in half so it's a physical. Isn't it still made of the same atoms? Aren't these atoms still what make up paper the same? Now, what if I take this paper and I light it on fire?
Do it, please.
That would be chemical, right? Because now the atoms are going up into smoke, they're going to form ash, they're changing the way those atoms are arranged, so you've done a chemical change. Okay, representing chemical reactions. Chemists use statements called equations to represent chemical reactions. So we're going to learn a lot about chemical equations. There's these things called reactants. And the reactants are the starting substances in a chemical reaction. That's what you're starting with. They are called reactants. Very important part to learn about in this chapter. Okay, so if you're starting with the reactants, well, you're going to make something. What do we call the substances that we make? They're called the products. The products are the substances that are formed in a reaction. So you produce something. They're called the products. You produce them. It's called the product. They are the substances that are formed, the ending result of a chemical reaction. So here's an example, guys, of a chemical equation. We've got aluminum plus bromine, and then we have this arrow. And then it has aluminum bromide. So where are the reactants? On the left side. I'm going to put a box around the reactants. My reactants are aluminum and bromine. What's my product? Aluminum bromide. So I'm going to put a circle around the product here. It's called aluminum bromide. So there's a couple of other things that we need to learn about. What does the plus sign do? It separates your reactant. So in this case, in this chemical reaction, we had two reactants. The plus sign just separates them. What does the arrow represent? Yeah, this is the chemical reaction. The arrow represents the chemical reaction. And then we form our products. And so that's how chemists would represent that reaction. Okay, there's some symbols, some other symbols. We just learned about the plus sign. It separates two or more reactants or products. The arrow separates the reactants from the products. This is what separates the reactants on this side. So reactants. And then it separates the reactants from the products. Sometimes you'll see a double-sided arrow. We'll get to that later in another chapter. Sometimes you'll see in parentheses a little s. What does the s mean? It's a solid. So if that substance is in the solid phase, sometimes you'll see a little parentheses subscript with an s in it. What does the L mean? It's a liquid state. G is in the gas state. And AQ identifies a water solution. AQ stands for aqueous, and aqueous means water. So if anything is dissolved in water, you'll see AQ there. Okay. Chemists use both word and skeleton equations to represent chemical reactions. You're supposed to write something there. Chemists use both word and skeleton equations to represent chemical reactions. So let me show you a word reaction. We'll differentiate between these two. In a word equation, it's spelled out. It's a word. So instead of using Al for aluminum, we spell it out. Bromine is spelled out, so this is just a word equation. It's just like reading words. Okay, well, the skeleton equation is a little different. Instead of writing out aluminum, like in the word equation, we'll use aluminum's chemical symbol, which is Al. What phase is this aluminum in, guys? It's a solid. What about the bromine? Liquid. And what about the aluminum bromide here? Solid. Okay. So both word and skeleton equations lack information about how many atoms are involved in the reaction. We'll talk about how they represent how many atoms are involved later. So we're going to practice writing skeleton equations from word equations. So hydrogen, what would I write here? Okay, we could put an H for hydrogen, right? What do I put for and? That's a plus sign. Bromine, what's bromine symbol? Br. And it says it reacts. What do I write for reacts? That's an arrow, okay? And it forms hydrogen bromide. Hydrogen bromide is HBr. And so wouldn't that be a way of going from the word to the skeleton equation? Sure. Okay. Let's do this one. Carbon monoxide is CO. What do I put for the word and? A plus sign. Oxygen is O. And then we see this word, react. What do I write? An arrow. And then it forms carbon dioxide. CO2 is what carbon dioxide is. Anyway, there's some introduction to how you write a skeleton equation. Chemical equations, you're supposed to write this definition down. Chemical equation is a statement that uses chemical formulas to show the identities and relative amounts of substances involved in a chemical reaction. So a chemical equation is a statement that uses chemical formulas to show the identities and relative amounts of the substances involved in a chemical reaction. We're going to spend the rest of the chapter talking about chemical equations. It shows us this chemical symbol, which represents its identity, and it also gives us information about the amounts of those elements that are in the chemical reaction. So we'll learn a lot about this stuff coming in just a minute. Here's an example. Okay, we've got aluminum plus bromine, and we've got an arrow, which means a chemical reaction took place, and it forms aluminum bromide. But what you're going to notice now, guys, is there's something different. How many aluminums do we have? 1. The number down here tells us how many we have. If there's no number, what's implied in chemistry? It's just a 1. So we see 1 aluminum atom here. Okay, if we react that with Br2, what is this 2 telling us? That there's 2 bromine atoms. So you'll see down here, there's 2 bromine atoms. If you react them, so you mix them together, they will do a chemical reaction and form AlBr3. How many aluminums? 1. It's just implied, so we don't write ones. How many bromines? 3. So you'll see 1 aluminum and 3 bromines. Okay? There's this very important property in chemistry. It's called the law of conservation of mass. I'm going to ask a lot of questions on the test about the law of conservation of mass. So please pay attention. This will be the last slide on this video. So law of conservation of mass. What does it mean to conserve something, guys? Like if you conserve water, what does that mean? You save it, right? So the law of conservation of mass means we're gonna account for all of the mass. We're gonna save it. Okay, the law of conservation of mass. Here's what it means. Please write this down. The law of conservation of mass says that in chemical reactions, mass cannot be created nor destroyed. Mass cannot be created, nor can it be destroyed. Mass cannot be created nor destroyed. So a lot of times students get confused by that because, like, what if I had this paper right here and I burned it? I mean, you could take this over to the scale, put it on the scale, and it has mass, right? But if I burn it, The law of conservation of mass says I can't create nor can I destroy mass. So where did the mass go when I burn it?
Into the air.
Smoke. Do the atoms that go into smoke have some mass? Yes, they do. If you could take all of that smoke, bring it back down and put it on the scale, and all the soot, would it equal the same mass as this paper right now? According to the law of conservation of mass, that's true. And that is true. Okay. That's right. Mass of reactants has got to equal the mass of the products that you form. It has to equal each other. So the mass of the reactants equals mass of products. Okay, so mass of reactants equals the mass of the products. All atoms on the reactant side must appear on the product side and in equal numbers. No new elements may appear. So if you don't have it on the reactant side, you can't just throw it on the product side. It has to be on both sides. And no elements may disappear. So if you have it on the left side, it's also got to be on the right side. Here's an example of what I mean. Here's something new. Okay, you see this 2 out in front? That's called a coefficient. How do we get the total number of aluminum atoms? We take the coefficient and we times it by the subscript down there. What is 2 times 1, guys? 2. So how many aluminum atoms do I have on the left side? 2. How many aluminum atoms do I have on the right side? 2. How many bromine atoms do I have here, guys? 3 times 2 is 6. How many bromine atoms do I have on the right side? 2 times 3 is 6. Okay, and so that's an example of law of conservation of mass. If I have aluminum over here on the reactant side, it's got to appear on the product side. If I have bromine on the reactant side, it's got to appear on the product side and in equal number. Now, here's the thing about chemical reactions that's cool. Aluminum and bromine on the reactant side are separated. They're different substances. But now we've done the reaction, and now we've formed a new compound, aluminum bromide. Is aluminum bromide going to have the same properties as aluminum or bromine? No, we made something new. This is going to have entirely new properties. That's what's cool about chemistry, is we can make new things. The new things have different properties, but we're using the same elements. We just rearrange them into something new. Does that make sense, guys? Okay. That's a pretty good introduction to chemical reactions. So hopefully you learned something. We're going to go in the next video and we're going to talk about how to balance chemical reactions, how to make the numbers on the reactant side equal the number on the product side. But hopefully that helps.